Great.
Hello everyone, welcome back. Today we are covering an interesting topic which is graph representation, specifically in adjacency list.
Great.
Hello everyone, welcome back. Today we are covering. Now let's get into the agenda. Here in our agenda we will talk about definition of adjacency list because we have to understand this first, and secondly in our agenda it says that representation of nodes and edges using list. We will look into this, and then examples with a simple graph for real time understanding, and last but not the least the comparison with adjacency matrix. I will explain this as well. Now let's understand what is a graph. So here it says that let's focus on left column. So when creating a left column, it says that a graph G consists of V, E vertices. So V equals set of vertices or nodes, and E is equals to set of edges or connections. In other words, so we have to understand always in graphs V means it's a set of vertices and E means it's sets of edges. And in the right column, we just need to draw a simple graph with four nodes A, B, C, D in a square formation. So it's what it is in the right column. A, B, C, D are the vertices. So this is an introduction for what is a graph. Right now, we will be moving into very important concept in our topic, today's topic. So which is that definition of adjacency list. So we have to specially understand this concept in order to move forward in this topic. So now let's understand what is an adjacency list. It is a collection of lists used to represent graphs. So each vertex in the graph stores a list of its adjacency vertices, as it says. And key characteristics of adjacency lists are space efficient. It's a big advantage. So if you want to use adjacency list, so you get an advantage. So you can determine whether you want to use an adjacency list or not based on these key characteristics. So it's space efficient and easy to iterate through neighbors. Space complexity is there, and dynamic and easy to add vertices and edges. So these are about the introduction for adjacency list, which is a key. Now let's get into visual representation from graph to adjacency list. So in this left side we have an undirected graph with vertices A, B, C, D, and this side, in the right side, we have the adjacency list. So before the right side, let's understand the left side graph. So in left side graph, we got something like this: A, B, C, and D. So this is how it has been represented. So we have to understand here is that A, here A is a vertex, and B, C, D all are vertices. So now here vertices A is connected to B and C, and vertices B is connected to A and D, and vertices C is also connected to A and D, and again vertices D is connected to B and C. So this is about the understanding of the left side of the graph, and when it comes to the right side, it's something like it depicts this. The same thing I will represent here, the right side. So it's like A, B, C, B, like A, D, and C as A, D, and D as B, C. So vertices A will has lists of B and C, and the vertices B will have in the adjacency list from A to D, and vertices C has lists from A to D, same, and vertices B will also have this from B to C. So this is about the understanding of visual representation from graphs to adjacency list. This side is the graph and right side is the adjacency list. So I hope you guys have got a very clear understanding of visual representation of graph and adjacency list. Here, now that we understood the adjacency list, now we will be understanding how we are going to implement this adjacency list in real programming. So we have two methods. Method 1 is array of lists and the method 2 is dictionary or using hash maps. So first we will be understanding how using array of lists we create adjacency list and implement it into the programming. So for that, for every vertices we put indexes. So of course in arrays the indexes comes into the player. So because of that, so we will be giving indexes for each vertices. So for vertices A, the index is 0. So it's 1, comma 2, which points to B and C, and to index 1 is vertices B. So it points 0, comma 3, it points to A to D. So it's like this, A to D, and index 2 it's vertices C. So it points to A to D. So vertices C, which points to A to D, and index 3 is vertices B. So it's 1 and 2, say. So it's pointing to B, comma C, as we understood earlier. Key is here is that using array, it's faster to access each vertices because of the indexes which array consists. Key is here is that using array, it's fast. Now let's understand the second method. It's dictionary or hash map. So in this, as you can see, there are A, B, C, D. So we can name the vertices as it is, and we are not limited to numbers unlike arrays. So in here, what it defines is that vertex A is mapped to B to C, and vertex B is mapped to A to D, and vertex C is mapped to A to D, and vertex D is mapped to D to C. So here we can use strings, we can use those kind of things to name it, and we never need numbers always. We are not limited to use only numbers. Here we can use like IDs, names, likewise. So that's the key advantage and key concept here using hash maps. We are not limited, unlike in array list we must use numbers, but here we can use strings, IDs, those kind of thing for vertices to name it. So this is about the hash map. Now,
since I am facing technical difficulty in the projector, so I will explain this slide this way. So first thing first, this slide compares two common ways to represent in memory adjacency matrix and adjacency list. So these two only we are going to compare. So number one, space complexity. So in the adjacency matrix, always needs v square space because it stores a full table even if there are very few edges. And when it comes to the adjacency list, under space complexity, it only stores actual connections, so it uses v plus e space, which is much more efficient for large graph. And the second one, checking if an edge exists. With a matrix, checking whether an edge exists is in big O of 1, or also we call it as constant time. Because we directly access the cell, but with an adjacency list, we must search through the neighbor list, which is big O of V in the worst case. So when it comes to the third one, finding all neighbors, in this, it's not much. It's to find all neighbors of a vertex in a matrix. So we scan the entire row that is big O of V in the adjacency list, but we only scan the connected nodes. So it is big O of degree, so which is usually much smaller. And the fourth comparison is adding and removing edges. So adding an edge is big O of 1, or like constant time. It's also known as adding an edge in big O of 1 is like both are same, but removing an edge is easy in a matrix because just it sets the value to 0, but in adjacency list it's not the case. We may need to search the list so it can take big O of v. And the fifth comparison is the when to use which. So overall, adjacency matrices are the best for dense graph, while adjacency lists are best for sparse graph, which is the case in most real-world application. So adjacency lists are mostly used than adjacency metrics, and that's why adjacency lists are mostly more commonly used in practices, especially in a large system like social network web pages. So this is all about the comparison part. I hope you guys got a clear understanding of adjacency list and adjacency matrix and their differences and what works well. So this is about it in this slide, under this comparison slide.
Now, let's understand the key takeaways from the concept that we have learned today. So, in the adjacency list, we have to understand the definition as we previously understood it. It's a collection of lists where each vertex stores its neighbors, and it's space efficient, and we discussed space efficiency in the comparison table. So the same thing here, and the third thing is that its key takeaway is the key implementation. It can use arrays, dictionaries, or hash maps, as we discussed earlier. And its trade-offs are it's better for neighbor iterations. This adjacency list is very good and choice, and its memory efficiency. So because of the memory efficiency, also this adjacency list is a good one, and but a disadvantage is that it's lower for edges existence checks compared to matrix. So this is about the key takeaways under the adjacency list. Thank you so much guys for listening. I hope I have given a clear idea about the graph representations using adjacency lists. I hope you all to see in another exciting video. Until then, goodbye from